Mathematics education faces a persistent frustration. Walk into almost any middle school math class, and you will find students struggling to grasp the actual nature of evidence and justification. Students frequently fall into an inductive trap, relying on empirical examples to justify mathematical truths, instead of constructing logical, formal, deductive proofs. Give a sixth grader a prompt like, "If you add any three odd numbers together, is your answer always odd?" And you will get responses exactly like this. Yes, because 7 plus 7 plus 7 equals 21. Those problems are proof that it is true. This chart tracks the percentage of middle school students relying on these empirical justifications across 3 years. The data shows a stubborn flatline. From 6th grade to 8th grade, roughly 40% of students continue treating isolated examples as definitive proof. A second line for the students who actually attempt a general deductive argument shows only marginal improvement. Even by the end of middle school, deductive reasoning remains a minority approach. From the perspective of the classroom, this data represents a developmental roadblock, a collective struggle to transition into formal, structural mathematical thinking. Stepping outside the mathematics department to look at data from cognitive science reveals a paradox. Where math educators see a failure to reason deductively, cognitive scientists see humans deploying incredibly powerful reasoning strategies. Traditional theories of development, like those of Jean Piaget, posited that children were limited to understanding obvious relations among observable properties. Modern cognitive science reveals a different reality. Children integrate complex statistical patterns to build sophisticated causal theories, evaluating evidence to make accurate inductive inferences about the natural world. By the time a student enters 8th grade math, they have accumulated thousands of successful experiences using empirical, inductive reasoning. They actively categorize living things by synthesizing data points about habitats, behaviors, and physical traits. Adolescents possess the cognitive hardware for complex reasoning. They are taking a strategy that succeeds brilliantly in the physical world and applying it to a formal, abstract domain where the rules of evidence are entirely different. Humans are reluctant deductive reasoners because daily survival rarely requires formal logic. Our brains are optimized for probabilistic testing, estimating the likelihood of an outcome based on available evidence. In the Watson selection task, participants evaluate the rule, if P is on one side, Q is on the other. To prove it, you must flip P and not Q. Yet in practice, most people select P and Q, testing information that simply matches the prompt. Oaksford and Chater argue this behavior represents optimal data selection. In the real world, checking instances where a rule might apply is the most efficient way to see if an idea holds weight. The success of this inductive testing rests on how a person represents similarity. Good conclusions require an understanding of which underlying traits make the objects in a sample related. Therefore, understanding why students lean so heavily on specific examples in mathematics requires finding out how they perceive similarity between mathematical objects. To map this perception, researchers conducted a multi-year study comparing 3 distinct groups: middle school students, college undergraduates, and doctoral-level experts in STEM fields. The participants were given sets of cards and asked to sort them into groups through 3 distinct tasks. First, sorting freely, adding to an established group, and deciding if new cards belonged.
Here is the visual array of the stimuli. The participants analyzed whole numbers ranging from 0 to 100, alongside a diverse set of geometric shapes. The experiment was designed to expose whether students attend to shallow features, like the count of digits, or deep mathematical features, like parity or primality. The data revealed that adolescent mental models are surprisingly aligned with those of STEM experts. This bar chart displays the numerical sorting data for parity, grouping numbers by even or odd. Across all 3 cohorts, parity was recognized as a primary structural feature by over 80% of participants. The alignment continued across other deep mathematical categories. Middle schoolers frequently organize numbers by their multiples and their prime status, matching the foundational categories used by the doctoral researchers. Students and experts alike largely ignored mathematically uninteresting features. Categories based on superficial traits, like grouping numbers simply because they both contain a specific digit, were rarely utilized by any group. Looking at the geometric sorting data, we see the exact same trend. Symmetry and the total number of sides were the most salient sorting principles for both the 12-year-olds and the engineers. There were a few areas of divergence. STEM experts showed higher sensitivity to shapes that were perfectly regular and numbers that were perfect squares, features the middle schoolers rarely prioritized on their own. The overarching pattern confirms that the cognitive architecture required for advanced mathematical reasoning is already online in young adolescents. They perceive the same deep structural similarities used by experts to write proofs. Educators can leverage these recognized deep structures, using a student's existing inductive instincts to build a bridge toward deductive proof. Humans evaluate the strength of evidence using specific criteria: amount, meaning a larger sample size; diversity, the use of dissimilar examples; and typicality, relying on representative cases. Instructors can guide students toward a general case by prompting them to test highly diverse examples, checking both evens and odds, or primes and composites. Mapping the edges of a pattern allows a student to naturally arrive at the threshold of deductive logic. Inductive reasoning relies heavily on negative evidence. While an empirical test cannot conclusively prove a mathematical conjecture, a single counterexample can conclusively disprove it, a natural gateway to teaching formal proof by contradiction. Methodologies like mathematical induction then serve as a way to systematize the empirical patterns the student is already actively seeking. Mathematics instruction can take this highly functional inductive engine and teach it to operate within the strict boundaries of formal proof. For decades, a student writing out 3 examples and calling it a proof was documented merely as an error. These students are actually operating as successful probabilistic reasoners, evaluating a domain of absolute certainty using the tools of likelihood. When a student chooses a specific number to test a theorem, that choice reveals their internal map of mathematical similarity. Educators who understand that map can guide the student toward the underlying structure. Refining this natural instinct facilitates the transition from induction to deduction. The student discovers that while evidence supports a conjecture, logic confirms it. The capacity for advanced mathematics is already present in the adolescent mind. To build the next generation of mathematicians, we simply have to learn to speak the language of the inductive mind.